wait. uh, wait, what? Test. Okay. So hello everyone. Yesterday I have read this entire chapter or like sub-chapter or whatever, but it was a silent stream. I was not talking or explaining like that rubber duck effect. And also I was extremely tired, but I had to stream because it's been like 3 days no stream. So anyway, I'm going to just reread it again, and while also taking some notes because here there is a lot to remember. Like what does the hardware do and what does the software do? Because there are some mechanisms that cannot be done only by software. Hardware must also be cooperative to make the execution run as fast as possible, like at hardware speed. No virtualization. The program runs directly on the CPU. Okay. What are we doing now? Now we are here in direct execution. Wait, limited direct, yes. Next chapter will be scheduling, a summary, address spaces, memory. Okay, so here the virtualization of the CPU, and here the virtualization of memory. Sounds good. Let's get going. I'll prepare first like some pen and paper. Okay, there we go. So in order to virtualize the CPU, the operating system needs to somehow share the physical CPU among many jobs running seemingly at the same time. The basic idea is simple. Run one process for a little while, then run another one, and so forth. By time sharing the CPU in this manner, virtualization is achieved. There are a few challenges, however, in building such virtualization machinery. The first is performance. How can we implement virtualization without adding excessive overhead to the system? Like, I think this means, uh, not I think, I'm pretty sure. Uh, it means like if you run a program like in a virtualized environment, like some virtual machine, there is some kind of translation. When you want to run a specific CPU instruction, it gets intercepted, then translated to the actual CPU instruction and run. This process adds some uh, significant overhead, I think. Just like when you compile something that to be running on RISC-V and you just run it on your x86 CPU, there should be some type of translation of of what? Of instructions. So we want to run programs on like without adding excessive overhead. So excessive means there would be some overhead, but it should not be excessive. Okay. The second is control. How can we run processes efficiently while retaining control over the CPU? Control particularly is important to the operating system, as it is in charge of resources. Without control, a process could simply run forever and take over the machine or access information that it should not be allowed to access. Okay. Obtaining high performance while maintaining control is thus one of the central challenges in building an operating system. Okay, so I have no idea how this is pronounced. The crux. Anyway, how to efficiently virtualize the CPU with control. The operating system must virtualize the CPU in an efficient manner while retaining control over the system. To do so, both hardware and operating system support will be required. Yep. So software alone is not enough. The operating system will often use judicious anyway bit of hardware support in order to accomplish its work effectively. Basic technique: limited direct execution. To make a program run as fast as one might expect, not surprisingly, operating system developers came up with a technique which called limited direct execution. The direct execution part of the idea is simple. Just run the program directly on the CPU. Thus, when the operating system wishes to start a program running, it creates a process entry for its process list. Okay, so when the operating system wishes to start a program running, it creates a process entry for it in a process list, allocates some memory for it, loads the program code in memory, locates its entry point, routine or something similar, okay, like main or underscore start, jumps to it and starts running the user code. Figure 6.1 shows this basic direct execution without any limits yet, using a normal call and return to jump to the program's main and later back into the kernel. Okay, so create entry process list, calculate memory for the program, load program in memory, set up stack with argc, argv, clear registers, execute main. Why clear registers? I guess some security mechanism. Like if a program just starts right at the bat and reads the registers, it might read some sensitive information left by the kernel, for example, or some other program, maybe. Okay. Execute call main. Run main, execute, return from main, free memory of process, remove process list. Okay, remove from process list. Sounds simple, right? No. But this approach gives rise to a few problems in our quest to virtualize the CPU. The first is simple. If we just run a program, how can the operating system make sure the program doesn't do anything that we don't want it to do while still running it efficiently? So the problem here is what? What is the problem? I have no idea. So the problem is we want to make the program that is running to run efficiently, like directly on the CPU. The operating system does not translate instructions to like find malicious ones and stop them from being executed. and yet not allow the program to do anything bad. The second, when we are running a process, how does the operating system stop it from running and switch to another process? Like thus implementing the time sharing we acquire to various CPU. This problem again is like if you have like let's say one processor and one CPU, one core, and one thread, for example, on a machine. So let's say the operating system started running a program. If that program was like doing some while loop, while true, like increment some variable and do some stuff that does not like make some syscall, uh, how do we even make the operating system take control again? Because if the program is running on the CPU, it means like the operating system is not running. So there must be some way to take the control back from the process and give it to the kernel. These are the main two problems we have in this chapter, I think. In answering these questions below, we get a much better sense of what is needed to virtualize the CPU. In developing these techniques, we will also see where the limited part of the name arises from. Without limits on running programs, the operating system wouldn't be in control of anything, and thus would just be a library. A very sad state of affairs for an aspiring operating system. Yeah, true. This is sad. The thing that was supposed to be the governor of the machine is just a library. Anyway. So the problem one, restricted operations. Let's see if there is a problem two. Switching between processes. Okay. Yeah, I have read this literally yesterday, and I cannot remember most of this stuff. What? Okay. Okay, so there is problem number one and problem number two. Fair. Where is it? Where is it? Okay. Direct execution has the obvious advantage of being fast. The program runs natively on the hardware CPU and thus executes as quickly as one would expect. But running on the CPU introduces a problem. What if the process wishes to perform some kind of restricted operation, such as issuing an I/O request to a disk or gaining access to more system resources such as the CPU or memory? How to perform restricted operations. A process must be able to perform I/O and some other restricted operations, but without giving the process complete control over the system. How can the operating system and the hardware work together to do so? Okay, aside, why system calls look like procedure calls? You may wonder why a call to a system call such as open or read look exactly like a typical procedure call in C. That is, if it looks just like a procedure call, how does the system know it's a system call and do all the right stuff? The simple reason, it is a procedure call, but hidden inside that procedure call is the famous trap instruction. More specifically, when you call open, you are executing a procedure call into the C library. Okay, wait, can we just find libc? What? To do a search or pop? Okay, I think this is it. Let me see again. Okay. So we have open fcntl. I think it's open. Open. Where is it? Where is it? Where is it? Okay, there is it. Okay, FCMGL. FCMGL, FCMGL, here is it. Create, open. Here is open. Well, I want to see the implementation actually. Namespace. Wait, what? So this is C++. What? Okay. Source. Kernel. ARPA. Init. So this is LLVM, I think it's just C++. Garbage. For embedded systems usage. Maybe we'll find something. String time std. Okay, let's see stdio. Printf. As printf. First start. stdio.h. Okay, let's see this. Okay, so there is nothing here. Oops. Okay, let's see this nozzle. Official user repository. Is there some kind of, I have no idea how to use this. It's tree. Okay. Include source. And non-regex resolute stdio. Pass printf. Oh my god. P open. Okay, so there is syscall. Sysclose. P1. Whatever. Okay, where's where? How much time? Okay, 23 minutes. Uh, like reading a book feels like you read a lot and you expect like it was 40 minutes and it's like only 20 or 15. But when you're actually coding, doing the fun stuff, the time passes so fast. Anyway, okay, where is it? If it looks like, how does the system know it's a system call and do the right stuff? The simple reason it is a procedure call, but hidden inside the procedure call is the famous trap instruction. More specifically, when you call open, for example, you are executing a procedure call in the C library. Therein, whether for open or any of the other system calls provided, the library uses an agreed upon calling convention with the kernel to put arguments to open in well-known locations on the stack or on specific registers. Puts the system call number into a well-known location as well, again into the stack, okay, and then executes the aforementioned trap instruction. The code in the library after the trap unpacks return values, and returns control to the program that issued the system call, and thus the parts of the C library that make system calls are hand coded in assembly, as they need to be carefully. Okay, what is this? Okay, yeah, whatever. As they need to carefully follow the convention in order to process arguments and return values correctly, as well as execute the hardware specific trap instruction. And now you know why you personally don't have to write assembly code to trap into an operating system. Somebody has already written that assembly for you. One approach would simply be to let any process do whatever it wants in terms of I/O and other related operations. However, doing so would prevent. Okay, wait. Um, okay, one approach would simply be to let any process do whatever it wants in terms of I/O and other related operations. However, doing so would prevent the construction of many kinds of systems that are desirable. For example, if we wish to build a file system that checks permissions before granting access to a file, we can simply let any user process the issued IOs to the disk. If we did, a process could simply read or write the entire disk, and thus all protections would be lost. Thus, the approach we take is to introduce a new processor mode known as user mode. Code that runs in user mode is restricted in what it can do. For example, when running in user mode, a process can't issue okay. Doing so would result in the processor raising an exception, and the operating system would then likely kill the process. In contrast to user mode, in kernel mode is kernel mode, which the operating system or kernel runs in. In this mode, code that runs can do what it likes, including privileged operations such as issuing I/O requests and executing all types of restricted instructions. We are still left with a challenge. However, what should a process do when it wishes to perform some kind of privileged operation, such as reading from disk? To enable this, virtually all modern hardware provides the ability for user programs to perform a system call. Pioneered on an ancient machine such as the Atlas, system calls allow the kernel to carefully expose certain key pieces of functionality to user program. I almost understood nothing here. Okay, wait. Okay, so the user mode is very restricted. It can only access itself, and that's it, and the resources that belong to it in memory. Mhm. Okay, what else? Code that runs in user mode is restricted in what it can do. For example, when running in user mode, a process can't issue IO requests. Doing so would result in the processor raising an exception. Mhm. The ICE would then likely kill the process. In contrast, okay, we are still left in with a challenge. However, what should a user process do when it wishes to perform some kind of privileged operation, such as reading from the disk? To enable this, virtually all modern hardware provides the ability for user programs to perform a system call. Pioneered with ancient machines such as Atlas, system calls allow the kernel to carefully expose certain key pieces of functionality to user programs, such as accessing the file system, creating and destroying processes, communicating with other processes, and allocating more memory. Most operating systems provide a few hundred calls. See the POSIX standard for details. Early Unix systems exposed a more concise subset of around 20 calls. To execute a system call, a program must execute a special trap instruction. This instruction simultaneously jumps into the kernel and raises the privilege level to kernel mode. Once it's in the kernel, the system can now perform whatever privileged operation it are needed, if allowed, and thus do the required work for the calling process. When finished, the operating system calls a special return from trap instruction, which, as you might expect, returns into the current user program while simultaneously reducing the privilege level back to user mode. I guess this is an atomic operation, like return from trap atomically returns to the user and reduce the privilege level. Mhm. Okay, let's read this first. We stopped here. The hardware assists the operating system by providing different modes of execution. In user mode, applications do not have full access to hardware resources. In kernel mode, the operating system has access to the full resources of the machine. Special instructions to trap into the kernel and return from trap back into user mode programs are also provided, as well as instructions that allow the operating system to tell the hardware where the trap table resides in memory. Okay, the hardware needs to be a bit careful when executing a trap. In that, it must make sure to save enough of the colors registers in order to be able to return correctly. When the operating system issues the return from trap instruction on x86, for example, the processor will push the program counter, flags, and a few other registers into a per processed kernel stack. The return from trap will pop these values of the stack and resume the execution of the user mode program. See the Intel Systems Manual, okay, whatever. Other hardware systems use different conventions, but the basic concepts are similar. Basic concepts are similar across platforms. There is one important detail left out of this discussion. How does the trap know which code to run inside the operating system? Clearly, the calling process can't specify an address to jump to. Okay, it makes sense. If you want to jump to some kernel address, it should be bad because you will just jump there anyway. Uh-huh. So that's syscalls table is something that the CPU knows about. When you do a syscall with like a number of 15 or whatever, the CPU will go to that syscall table and jump right into it, into the right address, and execute the code and then return back, as you would when making a procedure call. Doing so would allow programs to jump anywhere into the kernel, which clearly is a very bad idea. Thus, the kernel must carefully control what code executes upon the trap. Mhm. But let me understand something. You cannot jump from the user space to the kernel space because the kernel space is not in your allocated memory. So if you want to access it, then it will be bad. Like the program will just seek faults because you try to access a memory that was not allocated for you. So I think this paragraph talks about like making the mechanism like fundamentally related to the addresses. Like if you give it, for example, the address of if you allow it to jump to kernel space, then it will be bad. It will be bad because the kernel space might have some other functions or helper functions, for example, that you can just jump to and do whatever it wants. The kernel does so by setting up a trap table at boot time. When the machine boots up, mhm, it does so in privileged kernel mode, and thus is free to configure machine hardware as needed to as need be. Mhm. Thus is free to configure. Okay. One of the first things the operating system uh, thus does is to tell the hardware what code to run when certain exceptional event occurs. For example, the code should run when a hard disk interrupt takes place, when a keyboard interrupt occurs, or when a program makes a system call. Oh, this this is tough. Okay, so you must. It gets weirder. Like, what if in your laptop you had two keyboards at the same time, and both keyboards have two drivers? Like, each keyboard has a driver. Like, just thinking about this made me feel like operating systems is even harder than I expected to be. I knew it is hard, but you know, there are a lot of edge cases that you must account for. I mean, whatever. For example, what code should run when a hardware the operating system informs the hardware of locations of these track handlers. Usually with some kind of special instruction. Once the hardware is informed, it remembers the location of these handlers until the machine is next rebooted. And thus the hardware knows what to do. When the system calls and other expression, okay. Okay, so the OS at boot time, it is in kernel mode, initialize trap table, remember address of syscall handler. Okay, so creates entry for process list, allocates memory for program, loads program into memory, set up user stack with arg values, and fill the kernel stack with registers and program counter. Return from trap. Restore registers from kernel stack, move to user mode, jump to min. Run main, call system call, trap into operating system. Saves the registers to kernel stack, moves to kernel mode, jump to trap handler. Mhm. Hmm. Handle trap, do work of syscall, return from trap. Restore registers from kernel stack, move to user mode, jump to PC after trap. Okay, this does some work, then return from main on trap via exit. Free memory of process, remove the process list. Okay. Um, uh, how long have we been doing this? Okay, 43 minutes. We are close to earn our break. I mean, my break. You can take your break whenever you want because, you know, things work like that. Tip: beware of user inputs in secure systems. Okay. Mhm. Secure system must treat inputs. Okay, never trust user inputs. This is what this is about. To specify the exact system call number is usually assigned to each system call. The user code is thus responsible of placing the desired system call number in a register or at a specified location on the stack. The operating system, when handling the system call inside the trap handler, examines this number, ensures it is valid, and if it is, executes the correct responding code. This level of indirection serves as a form of protection. User code cannot specify an exact address to jump to, but rather must request a particular service via numbers. And the operating system defines the numbers, so I get what this means. And it cannot specify exactly what code to run on the kernel. For example, the open or write or send, for example, system calls. What do they do? What do they do? What do they do? They do something, and I don't know it. Yeah. So they for example, send system call will first, when you jump into the kernel, it will make sure you own that, like, those file descriptor is valid. You will like the buffer address is valid, and the length does not like make some kind of overflow. I mean, overflow in the user program is harmless for the kernel, but is harmful for your program anyway. But if it's like doing something harmful in the kernel space, it will just kill you, or like do some handle this problem, and you do not get to like choose whether you want to do these safety checks. So it's like when you go to a restaurant and you see a menu, you cannot choose exactly what you want in your food. Like, you cannot order some poison, for example, to hurt yourself or hurt someone eating with you, but you can order something on the table. You just tell the server, I have no servant, I think, or the waiter. Yes, waiter. You ask the waiter for a specific meal, and they will go prepare it for you. Like, ask the others to prepare it anyway. I think this is the idea. You tell the kernel what kind of thing I want to do, and it will do it for you. But you cannot specify, like, execute random code stuff on the kernel. You can only execute what the kernel allows you to execute. It's like a menu. Okay. I think I have this idea. Wait, no. Okay. Oh, wait, this is kind of good. No, this. we. Hmm. Why this is so thick? Like, why this is the minimum thickness level? Oh, so it's like okay, I understand what this is. Okay. Okay. Okay, whatever. Anyway, just a little production. One last side, being able to execute the instruction to tell the hardware where the trap tables are is a very powerful capability. Thus, as you might have guessed, okay, it is also a privileged operation. If you try to execute this instruction in user mode, the hardware won't let you. And you can probably guess what will happen. Adios, Oventin program. You will be dead in 20 minutes, in 20 nanoseconds. Point to ponder. What horrible things could you do to a system if you could install your own trap table? Could you take over the machine? Of course. The timeline with time increasing downward, it summarizes the protocol. We assume each process has a kernel stack where registers, including generic purpose and program counter, are saved to and restored from by the hardware. When transitioning into and out of the kernel, uh, there are two phases in the limited direct execution protocol. In the first, at boot time, the kernel initializes the trap table, and the CPU remembers its location for the subsequent use. The kernel does so via a privileged instruction. Okay, wait. The trap table and the CPU remembers okay. The kernel does so via privileged instruction. Okay. In the second, when the process, the kernel sets up a few things: allocation node on the process list, allocation memory before using a return from trap instruction to start the execution of process. This switches the CPU to user mode and begins running the process. When the process wishes to issue a system call, it taps back into the operating system, which handles it and once again returns control via a return from trap to the process. The process then completes its work and returns from main. Okay. What was the problem name? Restricted operations. So it's just like the kernel gives you a menu and you just choose whatever you want from the menu as long as you pass safe parameters and you're good. Okay. Switching between processes. The next problem with direct execution is achieving a switch between processes. Switching between processes should be simple, right? The operating system should just decide to stop one process and start another. What's the big deal? But it actually is a little bit tricky. Specifically, if a process is running on the CPU, this by definition means the operating system is not running. So you must somehow take the control back from the you know the what the what do you call it, the process. Okay, if the operating system is not running, how can you do anything at all? Hint: it can't. While this sounds almost philosophical, it is a real problem. How can you do the thing that you cannot do? There is clearly no way for the operating system to take an action if it is not running on the CPU. Thus, we arrive at the crux of the problem. How to regain control of the CPU? How can the operating system regain control of the CPU so that it can switch between processes? Okay, so this is the second big problem, which will be taking like the next 7 pages or 6, whatever. A cooperative approach. Wait for system calls. One approach that some operating systems have taken in the past, for example, every early version of Macintosh operating system, or the Xerox Alto system, is known as cooperative approach. In this style, the operating system trusts the processes of the system to behave reasonably. Processes that run for too long are assumed to periodically give up the CPU so that the operating system can decide to run some other tasks. Thus, you must ask, how does a friendly process give up the CPU in a utopian world? Most processes, as it turns out, transfer control of the CPU into the operating system quite frequently by making system calls. Uh-huh. Okay. Systems like this often include explicit yield system call, which does nothing except to transfer control to the operating system so it can run other processes. The applications also transfer control to the operating system when they do something illegal. For example, if an application divides by zero or tries to access memory that it shouldn't be able to access, it can generate a trap to the operating system. Okay. Thus, in a cooperative scheduling system, the OS regains control of the CPU by waiting for a system call or an illegal operation of some kind to take place. You might also be thinking, isn't this passive approach less than ideal? What happens, for example, if a process, whether malicious or just full of bugs, end up in an infinite loop? True. And never makes the system call what the operation can do then. Uh-huh. Uh-huh. Without some additional help from the hardware, it turns out the operating system can't do much at all when a process refuses to make system call or mistakes. And thus return okay. In fact, in the cooperative approach, your only recourse when this process gets stuck in an infinite loop is to resort to the age-old solution to our problems in computer systems. Reboot your machine. Thus, we again arrive at a sub-problem of our general quest to gain control of the CPU. Okay. So what I noticed is that this is like talking about process like it's a thread, and I have no idea why. But like you get the idea. How to gain control without cooperation? Even a process is not being cooperative. What can the operating system do to ensure a rogue process does not take over the machine? The answer turns out to be simple, as was discovered by a number of people building computer systems many years ago. A timer interrupt. A timer is a device that can be programmed to raise an interrupt every so many milliseconds. When the kernel is raised, when the interrupt is raised, the currently running process is halted, and the pre-configured interrupt handler in the OS run. At this point, the operating system has regained control of the CPU and thus can do what it pleases. Stop the current process and start a different one. As we discussed before with system calls, the operating system must inform the hardware of which code to run when the timer interrupts occurs. Thus, at boot time, the operating system does exactly that. Second, also during the boot. The boot sequence, the OS must start the timer, which of course is a privileged operation. Once the timer has begun, the operating system can thus feel safe in that control will eventually be returned to it. And thus the OS is free to run user programs. The timer can also be turned off, also a privileged operation, something we will discuss later when we understand concurrency in more detail. Note that the hardware has some responsibility when an interrupt occurs. In particular, save enough of the state of the program that was running when the interrupt occurs. This set of actions is quite similar to the behavior of the hardware during an explicit system call trap into the kernel, with various registers thus getting saved. And thus the easily restored by the return from trap instruction. Okay, changing application misbehavior. Operating system often have to deal with misbehaving processes, those that either through design or accident bugs attempt to do something that they shouldn't. In modern systems, the way the OS tries to handle such malfeasance is simply terminate the offender. One strike and you're out. Perhaps brutal, but what else should the operating system do when you try to access memory illegally or execute illegal instructions? Yeah, true. Like, if the world was like this, like an operating system, one mistake and you're out, it would be much safer. You know, just a thought. Saving and restoring context. Now that the operating system has regained control, whether cooperatively or via a system call, or more forcefully a time interrupt, a decision has to be made. So what is this decision? Whether to continue running the currently running process or switch to a different one. This decision is made by part of the operating system known as the scheduler. We will discuss scheduling policies in great detail in the next few chapters. Okay, we'll talk about the scheduler in the next few chapters. I shouldn't be worried about it right now, but okay. If the decision is made to switch, the operating system then executes a low-level piece of code, which we refer to as a context switch. Okay. A context switch is conceptually simple. All the OS has to do is save a few registered values for the currently execution process onto its kernel stack. Mhm. Uh, for example, and restore a few of the soon-to-be execution process from its kernel stack. By doing so, the operating system thus ensures that when the return from trap instruction is finally executed, instead of returning to the process that was running, the system resumes execution of another process. To save the context of the currently running process, the operating system will execute some low-level assembly code to save the general purpose registers PC and the kernel stack pointer of the currently running process, and then restore said register PC and switch the kernel stack for the soon-to-be execution process. By switching stacks, the kernel uh, enters the call to switch code in the context of one process, the one that was interrupted, and returns in the context of another, the soon-to-be execution. Okay. Tip: use the timer interrupt to regain control. The addition of a timer interrupt gives the operating system the ability to run again on a CPU even if processes act in a non-cooperative fashion. Thus, this hardware feature is essential in helping the operating system maintain control over the machine. Uh, okay. One, when the operating system then finally executes the return from trap instruction, the soon-to-be execution process becomes the currently running process. Wait, let's keep this like this. CPU scheduling. Let me open this. What this is about. Uh, multi. Okay, so this is like a manual for uh, for doing stuff, like for learning. Like it won't explain to you what are the program counter or stuff like that. So I should probably after finishing this PDF right here, I will be doing what I'll be learning about assembly. and the CPU registers, how they work, which are general purpose, which are not, um, what are some like sensitive registers, you know, things like this. Anyway, timeline of the entire process is shown is in figure 6.3. In this example, a process A is running, then is interrupted by timer interrupt. The hardware saves its registers into its kernel stack and enters the kernel switching to kernel mode. In the timer interrupt handler, the OS decides to switch from running process A to process B. At that point, it calls the switch routine, which carefully saves current register values into the process structure of A, restores the registers of process B from its process structure entry, and then switches contexts. Okay. Specifically by changing the stack pointer to use B's kernel stack and not A's one. Finally, the OS returns from trap, which restores B's registers and starts running it. Note that there are two types of register saves. Restore that happen during the protocol. First is when the timer interrupt occurs. In this case, these registers are implicitly saved by the hardware. Is in the kernel stack of that process. Okay, so this mechanism of having kernel stack and stack in general is something that is agreed upon with the hardware and cannot be changed. Like if you want to create the newest cool operation system. Okay, the user registers of the running process are implicitly saved by the hardware using the kernel stack of the process. The second is when the OS decides to switch. Okay, the kernel registers are explicitly saved by the software, but this time into memory in the process structure of the process. Later action moves the system from running as if trapped into the kernel from A, as if it just trapped into the kernel from B. To give you a better sense of how such a switch is enacted, figure 6.4 shows that the context switch code for XV6. See if you make sense of it. Shows the context switch code for XV6. See if you can make sense of it. You'll have to know a bit of x86 as well as to do so. The context structure of old new are found in the old new process structures respectively. Okay, interrupt table, remember addresses. Okay, start interrupt timer, interrupt CPU in X milliseconds. Okay, program is running now. Okay, timer interrupts. Saves the registers of A into the kernel stack of A. Move to kernel mode, jump to trap handler. Okay, handles the trap, call switch routine to save registers of A into process property A. Restore registers of B. Okay. Property B. Switch to K stack. Return from trap into B. Restore registers of B from the kernel stack. Okay, so the registers here should be, I think, put in the kernel stack of B. So the hardware takes them from the stack, puts them on the registers, move to user mode, jump to B's PC. No idea. Process B running now. Yep, I should learn more about assembly. Okay. Worried about concurrency? Some of you, as attentive and thoughtful readers, may be now thinking, what happens when during a system call a timer interrupt occurs? Oh, nice. That's a good question. Or what happens when you are handling one interrupt and another one happens? Doesn't that get hard to handle in the kernel? Good questions. We really have some hope for you. The answer is yes, does indeed need to be concerned about what to do if, what happens if during the interrupt or trap handling another interrupt occurs. This in fact is the exact topic of the second piece of this book on concurrency. Okay, we'll defer a detailed discussion until then. To whet your appetite, we'll just sketch some basics of how the OS handles these tricky situations. One simple thing an operating system might do is disable interrupts. During interrupt processing, doing so ensures that when one interrupt is being handled, no other one will be delivered to the CPU. Okay, this is I think this should be done only when there are timer interrupts, because what if a process okay, let me see this. Let me get the idea. So if what, so let's say if during syscalls you disable interrupts, timer interrupts, then a program can somehow do something like it will be run on the CPU and do some kind of syscall that does nothing, like sleep or something like that. Then sleep for like 1 millisecond, well, let's say 18 milliseconds, and the timer interrupt is done like no, it will cause sleep for like 1 nanosecond or so, and it will run it. It will send that like around that exact sleep instruction every like 10 milliseconds. If the timer interrupt is set to be run every 20 milliseconds, maybe there is something like you can time the sleep system calls. Um, sleep, time the sleep system calls to do what? To be run exactly when the timer interrupt will be run, you know? So you can ignore them, all of them. And your program will take over the CPU for the rest of the life. I didn't know how to word it well because I am not native English speaker, but whatever. User interrupt during processing. Okay. Okay, there is this context switch. You save some word into AX from the stack pointer. Okay. I think EAX is the one like referencing the kernel stack, I think. Of course, the OS has to be careful in doing so. Disable interrupts for too long could lead to lost interrupts, which in technical terms is bad. Operating systems have also developed a number of sophisticated locking schemes to protect concurrent access to internal data structures. This enables multiple activities to be ongoing within the kernel at the same time, particularly useful on multiprocessors, as we'll see in the next piece of this book on concurrency. Though such locking can become complicated and lead to a variety of interesting and hard to find bugs. Okay, so what was the problem again? Okay, switching between processes. Okay, so the first problem was what? Restricted operations. Like the answer is like you expose just a menu. The operating system exposes a menu to the process, and the menu you have to choose from it. The second one is where is it? Where is the second problem? Okay, this is problem one. Switching between processes. How does the operating system takes control back from the process, and it's like just timer interrupts. Okay, we have described some key low-level mechanisms to implement the CPU virtualization, a set of techniques which we collectively refer to as limited direct execution. The basic idea is straightforward. Just run the program you want to run on the CPU, but first make sure to set the hardware as the limit so as to limit what the process can do without OS assistance. This general approach is taken into real life as well. For example, those of you who have children, okay. Okay, so how long context switches take? A natural question you might have is how long does something like context switch take, or even a system call? For those of you that are curious, there is a tool called LM that measure exactly those things, as well as a few other performance measures that might be relevant. The results have improved quite a bit over time, roughly tracking processor performance. For example, in 1996, run Linux okay on 200 megahertz P6 CPU system cost roughly 4 milliseconds, and the context switch roughly 6 milliseconds. Okay, so microseconds. Okay, so 4 microseconds, context switch 6 microseconds. Modern systems perform almost on an order of magnitude better. With sub microseconds result, okay, sub microsecond result on the system with 2-3 gigahertz processor. It should be noted that all the operating system actions track CPU performance. As Austrich observed, many operations are memory intensive, and memory bandwidth has not improved as dramatically as processor speed over time. Thus, depending on your workload, buying the latest greatest processor may not speed up your OS as you might hope. Okay, okay, so this is like okay. I think I should take some rest now. Yeah. We are so back. Anyway, so we stopped here. This aside, key CPU virtualization terms, mechanisms. The CPU should support at least two modes of execution: a restricted user mode and privileged kernel mode. Typical user applications run in user mode and use a system call to trap into the kernel to request operating system services. The trap instruction saves the register state carefully, changes the hardware status to kernel mode, and jumps into the operating system to a pre-specified destination, the trap table. When the operating system finishes servicing a system call, it returns to user program via another special return from trap instruction, which reduces privilege and return to controller after the trap. Okay. The trap tables must be set up by the operating system at boot time and make sure that they cannot be readily modified by your user program. All of this is part of the limited direct execution protocol, which runs programs efficiently but without loss of OS control. Once the program is running, the operating system must use hardware mechanisms to ensure the user program does not run forever, namely the timer interrupt. This approach is a non-cooperative approach of the CPU scheduling. Sometimes the operating system during a timer interrupt or a system call might wish to switch from running the current process to a different one, a low-level technique known as context switch. Okay, homework measurement. Okay, so this measurement homework is a small exercise where you write code to run on a real machine in order to measure some aspect of the OS or hardware performance. And the idea behind such homework is to give you a little bit of hands-on experience with the real operating system. In this homework, you will measure the cost of a system call and context switch. Measuring the cost of a system call is relatively easy. For example, you could repeatedly call a simple system call, performing 0 byte read, and time how long it takes. Dividing the time by a number then gives an estimate of the cost of system call. Okay. One thing you'll have to take into account is the precision and accuracy of your timer. A typical timer lets you that you can use is get time of day. Read the map page for details. What you'll see there is get time of day. Returns the time in microseconds since. Okay. However, this does not mean that the timer is precise to the microsecond. Measure back-to-back calls to learn something about how precise the timer really is. This will tell you how many iterations of your null system call test you will have to run in order to get a good measurement of result. If get time of day is not precise enough for you, you might look into RDTSC instruction available on x86 machines. Okay, I'll just copy this and ask ChatGPT. Explain me this stuff here. Uh, no, 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 no. Medium. Just select GPT 5.5. What? Okay. Micro benchmarking, measuring very small costs, like how long does the system call take, or how long does a context switch take. The tricky part is that the thing you are measuring takes only tens. Wait. Measuring may take only tens or hundreds of milliseconds, so a timer might not be accurate enough to measure one operation directly. Measuring a system call. A system call when your program asks the kernel to do something. Okay, a normal function stays in user space. System call crosses from user mode into kernel mode. Does some kernel work, then returns to user mode. That transition has overhead. The homework suggests measuring a chip small, uh, for example, 0 by 8. Because count is equal to 0, the kernel does almost no real I/O. So the measured uh, time mostly reflects the syscall overhead itself. Suppose the syscall takes around 200 milliseconds. If your timer only changes every 1 microsecond, then your system call so timing one syscall is useless. You might get okay, which looks like 0 time. Instead, run many iterations. Get time of day. Okay. Returns the wall clock time. This does not mean the timer is precise to the microsecond. Okay, that suggests that the timer changes in chunks. Okay. Okay, let's see. Okay, this the time of the system system.h. What should we do now? Struct time zone. I think this is the one. Wait. Time val. Okay, time val. T1. Two. Okay. The time of day. T1. What? No, okay. No. Printf microseconds T1, okay, T2 dot microsecond minus T1 dot T but type what? How did the caps lock even get activated? Okay, long, okay. Okay. Okay, so all of them 0 microseconds. You sleep 1 microsecond. What the hell? Right, I should recompile. Oh, I think USleep is a system call also. So here there is the context switch. Wait, no. This cannot be true. Microseconds until signal arrives. I think this is not what we want. Okay, read. We are going to read from S to the N final argv 0, something like this. Which 1440. Okay. Precision versus accuracy. Uh, okay, let's see. Let's do this like normal function, void no op return int x, something like this. Now define n1 1 2 3 1 2 3. Okay, 10 million times, 10 million iterations. Okay, for int I is equal to 0, I is less than n I plus plus. What? Struct time var g1 g2. Get time of day g1 null read. Let's do the in file now. RV 0. Total time. uh-huh. And total time plus equal t2 dot k minus t1 dot k c square dash time total time divided by n. Okay, this is this. Please copy this again. Put it here again. Let's reset total time. Let's make it equal to 0. And okay, like this. And here, let's do this more up. Okay, let's just run. Syscall average time 0. Okay, this is weird. Maybe I should compile with debug and zero optimization. Okay. Let's see. If you want to segment. Oh my god. And let's Wait, let me try. I don't think this is a problem, but yes. Oh, I get it. Oh my god. I should. Oh my god, that was stupid for me. I should take this and put this here after finishing. And total time is going to be put here. Okay. Just assignment. Just to make this clean. Okay, I have no idea what this does, but I'm going to just do it anyway for now. Wait. I'm going to just do this. Put okay, 1 million. Okay. Syscall, okay. Okay, let's run this. I hate initial. Okay, so 88 nanoseconds. 1 nanosecond. Okay, before I continue, I have a question about this. When you cast some integer to double, does this get transformed? Okay, let's run it again. Almost same thing. 1 nanosecond, 80 or 90. Okay, but what if I compile with 0 optimizations? Same thing, optimization doesn't do anything. Okay, it does actually. The cost of a normal call got increased significantly. Okay. Wait, I should do here some sleep for 1 second because to prevent the cold starts thing. Okay, 90 nanoseconds, almost 2 nanoseconds. Okay, what if we compile with this with optimization? Yes, the optimization reduces the average call time a lot. Anyway, yes, in C when you cast an integer to double, the value is converted into machine floating point representation. Another one, okay, is called double. So casting is not like just for the compiler's sake. I get it. What is this? Okay. Okay, I get this. Okay, so we take the seconds, multiply them by a million to get microseconds, then add microseconds difference. Remove this, remove this. Okay. Okay. Measuring the cost of a context switch is a little tricky. The Lambench benchmark does so by running two processes on a single CPU and setting up two Unix pipes between them. A pipe is just one of many ways processes in a Unix system can communicate with another. The first process then issues a write to the first pipe and waits for a read on the second. Upon seeing the first process waiting for something to read from the second pipe, Lois puts the first process in a blocked state and switches to the other process, which reads from the first pipe and then writes to the second. When the second process reads from the first pipe again, it blocks and thus here the back and forth cycle communication. By measuring the cost of communication like this, base customer context switch, you can try to recreate something similar here using pipes, perhaps some other communication mechanisms and Unix extensions. One difficulty measuring the context switch cost alloys and systems more than one CPU. What you need to do on such a system is ensure that your context switch inputs are located on the same processor. Fortunately, most operating systems have calls to bind a process to a particular processor. On Linux, for example, a skill set affinity call is what you're looking for. By ensuring processes are on the same processor, you are making sure the measurement correct. Okay. Okay. I'll just read in final argv 0. Can I just pass here now because it's not going to try to do references anyway, unless it's stupid. Something like this. Okay, now it's 200 nanoseconds. 200, so the time jumped like, oh my god, this is a lot. This is like 150 times like slower or something. I think this cost is just from like the safety checks and all that stuff, maybe. Which right let's try this. Okay, again 200 nanoseconds. What? Okay, let's try something else other than read and write. Let's do int wait socket ARPA init. Let's now have socket int domain. What was the domain? Address found, I think. Init type so string protocol 0. I think this is wait, I think this is going to crash. Wait. Like this was allocating a lot of essential file descriptors. Int fd is equal to this, and we're going to close fd. Now we have two syscalls. What we are going to do, divide by 2n. Two times surrounded by this. Okay, let's try again. Is this correct? We create a socket file descriptor and we close it. So we have two. Yes, it is two. Oh my god. 1 microsecond. 1.5 microseconds. So syscalls are way expensive, like way expensive. That's it's asking if it's correct, everything's good. Okay, let's try with optimization. was 200 is now this. So this is not cheap enough. Does it camera? Okay. Yes, I was stupid. Okay. Anyway. Okay, this one is finished, I think. No, not yet. I need to measure the process context switch. So just syscall context switch. Okay, then something like this. What? Oh. Syscall context switch. Okay, let's create syscall overhead. There is no syscall context switch in it. Okay, process context switch. Let's see. Let's do again thread context switch. Let's do into main. Something like this. Socket pair. Of Unix type. No idea, put here 0, 0, FDs, int FDs 2. case there is this call create an unnamed pair of connected sockets in the specified domain of the specified type and using this optionally specified protocol. For further details of these arguments, see socket. Wait, there is this. Sock. How to open a simple Linux socket or socket stream. Okay. Okay, so stream. Okay, what if you put sock diagram there? Okay, whatever. I think it should be did like this. There is no void pointer. Pinger void arg. And we'll have also ponger. Return no what? Okay. Thread create. Okay. Create G1 decimal pinger FDs thread T1 T2 long if it is +1. Okay, thread join T1 null. Okay, let's do this. So wait. It should read from one and write to the other. Set socket if it is 0 level socket of name sock no I don't remember, so just do this. How do I make it not buffer anything for them already? Something I want to use this to measure thread context switch. Okay, the usual trick is to force the two threads to block and wake each other in a ping pong pattern. That's what I did. Okay, I did not ask you to do this. I'm just going to do this. I don't need this. Wait. Okay. Int if this is equal to arg pointer arg. Define and 1 2 3 1 2 3 1 2 3 1 2 3 and 10. Okay, 10 millions. For each I is equal to 0, I is less than m, I plus plus. I just realized I could just do this in one thread. The main thread is the pinger and the other one is punker. Anyway, doesn't matter. I just refactor it later. Right. It is 0 x 1, something like this. I'll just read f is 1 buff 1. Okay. Just copy this, put it here. I think I just do it 1 million times. Let's put this here. What? TV. long will while one it will do what? It will read from fds 1 into above, and the size of this buffer is 1. And it will write 0 So this right, there is this problem which must whatever, just put this here. Wait, where is it? It's got in std. What the fuck? What is this called? What is this? The inch. What? Oh my gosh. Why did this crash? But there is this thing here. Wait, so what do we write, then we switch to the other one, then the other one reads and writes back, and we switch here. And so here it should be divided by 2. Uh, 2 times n. Wait, what? Uh, 600 nanoseconds. Uh, I'll just copy the first part here. thread context switch. Okay, copy this. Put it here under main. I'll have this. Wait. في مشكل. Okay, and this is double. What? Six hundred nanoseconds. Okay, what about 10 million? Okay, so 10 million is the same. So I'll just copy this and put it here. And of course, I just have to copy this. Just copy all of them. Put them here. Put them here. Watch. Put it here. 50. Where is it? Okay, so I create this designs. We launch the thread. Okay, we do this. Okay. Just copy it and put it here. Okay. Put them here. Okay. Okay, so we measured normal count, we measured the thread context switch average time. Minus syscall time s. Syscall. Okay. Okay, I think 10 million times is a little bit too much, maybe. Yeah, it's taking too long. Okay, just do 1 million time only. Okay, now it's completed so fast. Oh my god. What? What if it should take only 10 times this amount? Or 20 times, oh, 20 times the same amount of time. Okay, whatever. Hmm. Is not reliable because there are several bugs and measurement issues. Wait. I'm good. One. Oh, I get it. Wait. I should read from the first one something. Okay. Um, yes, that was stupid from me. And here should be 0. Is this something else? Should be okay. Oh, I should subtract. And just remove this and remove this. Wait, there is 4 syscalls. The difference, so there is this difference. The difference has the 2 context switches and 4 syscalls. Wait, let me read this. Longer. So ping pong time. I don't understand this. Round trip ns minus 2 times this. Round trip round trip. There are, okay, here it is 4 into wait, 1 2 3 1 2 3 okay, just 1 million times so it doesn't take forever. Is the right final formula method clean up or wrong? Who said I want to clean? Oh, wait. Task set C0. What is it? Task set C0. Okay. Main problem is the but each round trip contains 4 socket syscalls. Okay. Round trip is equal to 4 socket syscalls plus 2 wake up context switches. Yes. If you round trip divided by 2 minus 2 minus syscall. No. Better T2 is unused. Yeah, of course, man. Where is T2? Okay, this one doesn't matter. You here. Oh my god, algebra. Oh my god, this guy is so stupid. The issue is whether the model behind the formula is valid. Okay, whatever you say, bro. The weaker assumption is that you measured system call. Yes, man. Let's copy this and see what this will give us. Put here. One, two, three, one, two, three. Why this one is so fast? Has the no up syscall. Okay, this one is get speed. Um, I think this is enough for this homework. The process context switch, I think I should be doing it later on, or maybe not. Mhm. Okay, we finished this direct execution. Now CPU scheduling. Cisco thread focus process context switch overhead benchmark. Let's see if some people already did the job for us. Okay, let's read this. Just because we got the thread context switch. Okay. What is this? Oh, it's go. Okay. Threads of the same processes get different IDs. Do not confuse them with different processes. So a process is just a thread. A thread is a process with some. Okay, they share the same address space and stuff. This. Can you just give us some graphs? Uh, what? You know what? Just. Okay. Okay. Scheduling. Oh, wait, before that, I want to learn a little bit more on assembly to know exactly what happens during context switches and syscalls, of course. Give me a quick refresh on risk 5. Typical instructions. Not all of them, just enough. I am refresh. Okay, this is destination, source 1, source 2 are immediate. Stack pointer, function arguments, return values. Temporaries, Kali saved registers. Arithmetic. Alright, comparison results as 0 or 1. Less than and immediate. Loud. Store double word. Loud word forward. Okay. Double is 8 bytes, word is 4 bytes. Offset base register. This one is just like memory stack pointer plus 16. So this is like just dereferencing. Yes, this is dereferencing. I don't know if I should learn this in x86 or Mhm. Most Linux documentation examples targets. Okay, we'll count encounter and constantly. Okay, focus first on System V and IMG 64 API. Return value A0. Wait, so in RISC-V you can return two values? Is that it? Can I save the temporaries? Can you save the return address stack pointer? Hmm. What should I do now? Intel syntax. Handling this later. Be right back. Okay, we are back. So I was asking about like learning this stuff about assembly, x86 Intel syntax. A B C D S. Wait. S D B S B. What? RSI, RDI, RVP, RSP. Okay, this is base pointer and this is stack pointer. These ones, okay, from R8 to R15, A, so this array, RIX, RAX, RBX, RCX, RTX, RSI, RDI. Okay, whatever. You know what? I don't really need all of these. I just want to understand what each register does, so I understand context switching better. What the CPU does when a syscall is made and stuff like this. Which registers are saved, which not, which is for the privilege level and so on. These hold ordinary program data. Okay, everyone that starts with R, probably. No, but there is, I think, still R1, R2, maybe. Okay, return value, I know. RCX, okay, stack pointer, frame pointer. Color saved, okay. Colors, whatever. These color coding rules matter for normal function. Okay. The important control registers. RIP, instruction pointer, asterisk address of the next instruction. When the execution resumes, the CPU continues from the restored RIP. RIP, stack pointer. Okay. Contains status and control flags. R flags. Zero flag, carry flag, interrupt enable flag, and the important one for the interrupt is often IF. Interrupt enable flag. Segment registers. Okay. In 64-bit mode, segmentation is largely disabled, but these still matter. Okay, see us as the current code and stack privilege context. FS and GS are commonly used for thread local per CPU data. User space FS base often points to the thread local storage. Rings 1 and 2 are generally unused widely Linux. So when people say CPU entered kernel mode, the CPU has switched to code executing with CPL0. CR0 control modules populations. Page generated behavior rights protection protected mode. Your kernel entry code must handle the rest. Entry Linux CPU records structure. Okay. General purpose registers. Original syscall number. Read say as flagged or as PSS. There is a lot here to learn. Also change the context switch. um, just play because this is tough to learn. Uh, okay, 70. At first it was 78, 30, 80, 80, 80, 80. Then here started decreasing. Beneficent moisture. Nice. Assembly entry code saves the general purpose registers into struct ptrex. SIMD FPU registers are not normally saved on every syscall or interrupt. Okay. For the 64-bit syscall instruction, the CPU does not push a frame onto the stack. CPU perform RCX. RIP. After syscall instruction. Oh, so the kernel uses RCX to store the return instruction pointer. Kernel entry address, kernel code selector, kernel stack selector. Code selector, stack selector. Okay, it also does not automatically switch to the task's normal kernel stack. Linux initially records the user stack pointer, switches address space, and loads the kernel stack itself. Current Linux entry code stores RSP, switches to the kernel stack, and manually constructs a ptrex frame. Saved by Linux. Synthetic user SS copied from RCX. RIP, RSCS, RLS, RSPSS. So for an interrupt from user space. Okay. ABI cannot write it with move, but you control it directly through jump flags. User program can read many flags and notify some of them. You can affix flags. Okay. Simultaneous flashing point instructions. You can preserve this state across scheduling. Segment registers. User space can access and with restrictions. I don't know what to do right now. Should I just now learn the theory, then go to the XV6? Then go to XV6 and do stuff? Or like do both at the same time? I don't really know. Wait. It's here. What is it? Extern. Extern switch. Okay, switch.s. Okay, so here is this. For example, scheduler for okay, switch context proc CPU. What? Oh, so you take with the context. I remember maybe there is some switch. Okay. So the old is first. So you take it from the CPU, and then you put it in context in this process proc. Release from 0. Okay. Nothing to run. Stop running this call until interrupt. What the hell is this notation? Type here, oh my god, and 2. The 2 level indentation. Here is 2. Okay, so I'll just do this. Nice. And then let's search switch. There was this, for example. Okay, here. Oh, wait. Press. Okay. I remove the Clang format. Kernel unlock. What? CP hosting formats. Why? Whatever. No idea why. Indent width 8, tab width 8, use tab never. Continuation indentation width 8. Okay, now it's good. What is Amazon long format? No. Remote shell. Where is it? Protocol. See. Okay. Okay, whatever. Git commit okay, like this. Okay, whatever. So we finished this one. It's just cd project move experiments to syscall context switch over something like okay. CPU scheduling. Okay, 13 pages, not by now non-living mechanisms of running processes. Okay, now I'll just skip the implementation details for now. I just know that when you want to context switch, you just push some registers. When you use a syscall, you push also some registers. They may differ, but whatever, it's whatever. That's why I'm going to wait and read the theory first, then I'll jump into the code. And then okay, so biology both those age this uint. Okay, there are a lot of errors somehow. H breathe. Use of undeclared undefined unit. It's whatever. Rotary scheduling code. MLFQ, multi-level feedback queue. Rotary scheduling, multi-assembly. CD main.c main. What do we do? 24,000 is equal to 9, something like this. I think this should not do a random sigfold. Maybe. Maybe. Just segmentation fault. Why? Oh, I think I understand why. It's because the stack pointer grows downward and we want to okay, so we try to access something. Okay, what if I do minus? Okay, did not even sigfold. Okay, nothing. What if I make it 9,000? Wait, come on. Nothing, but if I make it positive, it will be a sigfold. Definitely. Yep. So I think this is because the stack size is usually 8 megabytes. Okay, so what if we do 24 times 24 times 7? Segmentation fault, so it's too much. Wait, still, it's whatever. I just for now do char pointer and equal to malloc 1. I had 20. Okay, just do 4,000 is equal to 9. That's right. Nothing is wrong here. Okay. 90 should not say false. 95. Nothing. 96. Nothing. But 97 is probably will be sigfold. No, it did not. So this one, let me try something like 9,000. Still not. Okay. Malloc. With size 1 will allocate 1 4 kilobytes each for my process. Small chunk from the existing heap arena. The chunk is larger than 1 byte because the alignment. Okay. More heap. How's this? Mainland elsewhere inside the process currently mapped the heap region. Neither address necessarily cross into non-page. CPU has no reason to raise page fault. The allocation boundary is known to malloc, but not enforced by MMU. Wait. Oh, 0. Whatever. Hmm. Uh, anyway. Hmm. So it's 5 hours and 10 minutes. Let's see. Okay, 45 minutes. Be right back in 5 Okay. Um, the by now low-level mechanisms of running processes, context switching should be clear. It is clear, kinda. If they are not, go back to chapter two. Go back at chapter 2 and read the description of how the stuff works again. However, we have yet to understand the high-level policies that an operation system scheduler employs. We will now do just that, presenting a series of scheduling policies, sometimes called disciplines, that various smart and hardworking people have developed over the years. Uh, I think from what I have seen that mm, this book is almost 700 pages, and what 700 pages of theory. Would I be able to read all of it before I start touching the code? Maybe I should just learn theory. I have no idea, honestly. Hmm. By now, low-level mechanisms of running processes should be clear. If they are not, go back a chapter or two and read the description of how that stuff works again. However, if we have yet to understand the high-level policies that an operating system scheduler employs, we will now digest. Okay, present a series of scheduling policies, sometimes called disciplines, that very smart and hardworking people have developed over the years. The origins of scheduling, in fact, predate computer systems. Okay. Early approaches were taken from the field of operations management and applied to computers. Okay, this reality should be no surprise. Assembly lines and many other human endeavors also require scheduling, and many of the same concerns exist therein, including a laser-like desire for efficiency. And that's our problem. How to develop scheduling policy? How should we develop a basic framework for thinking about scheduling policies? What are the key assumptions? What metrics are important? What basic approaches have been used in the earliest of computer systems? Okay, workload assumptions. Before getting into the range of possible policies, let us first make a number of simplifying assumptions about the process running in the system, sometimes collectively called the workload. Uh, Determining the workload is a critical part of building policies. And the more you know about workload, the more you fine-tune your policy can be. Okay, the workload assumptions we make here are mostly unrealistic, but this is alright for now, because we will relax them as we go, and eventually develop what we will refer to as the magic pose, a fully operational scheduling discipline. We will make this following assumption about the processes, sometimes called jobs, that are running in the system. Each job runs for the same amount of time, All jobs arrive at the same time. Once started, each job runs to completion. All jobs use only the CPU. Okay, performance area. The run time of each job is known. Uh-huh. Each job, okay, we make different assumptions, okay. But just as some animals are more equal than others, okay, some assumptions are more unrealistic than others in this chapter. In particular, it might bother you that the runtime of each job is known. This would make the schedule omniscient, which, although it will be great, probably, is not likely to happen anytime soon. Each job runs for the same amount of time. All jobs arrive at the same time. Once started, each job runs to completion. All jobs use only CPU. Okay. Uh, each job runs for the same amount of time. So each program schedule metrics. Beyond making workload assumptions, we also need one more thing to enable us to compare different scheduling policies. A scheduling metric. A metric is just something that we use to measure something. Uh, what do we measure? Okay. Okay, we measure something, but what is this something? And there are numbers of there are a number of different metrics that make sense in scheduling. For now, however, let us also simplify our life by simply having a single metric: turnaround time. The turnaround time of a job is defined as the time at which the job completes minus the time at which the job arrives at the system. More formally, completion arrival. Okay, so just the duration of runtime, I guess. Hmm. Because we have assumed that all jobs arrive at the same time for now. T arrival, okay. Advance turnaround is T completion. The fact this fact will change as we relax the aforementioned assumptions. You should know that the turnaround time is a performance metric, which will be our primary focus in this chapter. Another metric of interest is fairness, as measured, for example, by Jane's fairness index. Okay, by Jane's fairness index, performance and fairness are often at odds in scheduling. A scheduler, for example, may optimize performance but at cost of preventing a few jobs from running, thus decreasing fairness. The conundrum shows us that life isn't always perfect. Okay. The most basic algorithm we can implement is known as first in, first out, FIFO. Scheduling is sometimes for first come, first served. FIFO has a number of positive properties. Wait, I'll just answer a message. Anyway, so okay, so FIFO has a number of positive properties. It is clearly simple and thus easy to implement. And given our assumptions, it works very well. Let's do a quick example together. Imagine three jobs arrive at in the system A, B, and C at roughly the same time. Because FIFO has to put some job first, it assumes that while they are live simultaneously, A arrived just a hair before B, which arrived okay. Assume also that each job runs for 10 seconds. What will be the average turnaround for time for to be for these jobs? 10? It will be 10. Okay, what is average turnaround time? What? Turnaround time. What do they mean by that? I don't understand why this average turnaround time is important. It looks stupid if you have just many jobs, it will be uh, higher. Okay. Okay. Now let's relax one of our assumptions. In particular, it's assumption one. Let us no longer assume that each job runs for the same amount of time. How does FIFA perform now? What kind of workload could you construct to make FIFA perform poorly? Uh, I just saw this. So it's just the same thing. You run the longest one first. If you run the longest task first, the other ones will stop. It's just like um, when you want to buy something in a supermarket and you want to buy only like some cookie or something like that, and there is sometimes someone in front of you who has like uh, two baskets full of things to buy, and it takes 20 minutes just to process that stuff and pay. So you just waste there for 20 minutes just to buy something that is worth half a dollar, for example. Yes. Okay. Think about this before reading. Okay, presumably you figure out them, but just in case, let's do an example to show how jobs of different fronts can lead to trouble if in for people scheduling. In particular, let's again assume three jobs A, B, and C. But this time A runs for 100 seconds while B and C run for 10 each. Um, Okay, as you can see, job A runs first for the full 100 seconds before B or C even get a chance to run. Thus, the average turnaround time for the system is high. Uh-huh. The problem is generally referred as convoy effect. Chain. Y is schedule average turnaround time is important. Seems stupid metric. Uh, maybe, okay, whatever. So the average turnaround time is just expected like estimation of the expected value. Uh, for example, when you run some random program, how long will it take to actually finish? This problem is generally referred to as the convoy effect, where a number of relatively short potential consumers of a resource get queued. To the benefit of SGF. Right. This problem is generally referred to as convoy effect, where a number of resources get queued behind a heavyweight resource consumers. Scheduling scenario might remind you of a single line of grocery store. And what you feel like when you see a person in front of you with three carts? Yes, carts is the word I was looking for. I said baskets. Anyway, full of provisions. It's going to be a while. So what should we do? How can we develop a better algorithm to deal with our new reality of jobs that run for a different amount of time? Think about it first, then read on. Uh, yes, I thought of it, or I read it here before. Yeah, the shortest job first represents the general scheduling principle that can be applied to any system where the perceived turnaround time per customer, or just in case job, matters. Think of any line you have waited in. If the establishment in the question cares about consumer satisfaction, it is likely they have taken SGF into account. For example, grocery stores commonly have 10 items or less. Line to ensure that shoppers with only a few things to purchase don't get stuck behind the family preparing for some upcoming winter. Yes. Okay. Okay. It turns out that a very simple approach solves this problem. In fact, it is an idea stolen from operations research and applied to scheduling of. Okay. This new scheduling discipline is known as shortage job first, and the name would be easy to remember because it describes the policy quite completely. It runs the shortest job first, then next shortest, and so on. Let's take our example above with SGF as our scheduling policy. Okay, shows the result. Okay, makes it clear. Okay, down to 50, more than a factor of 2 improvement. Recommend action in this case: either quickly switch to different line, or take or take a long, deep, and relaxing breath. That's right. Breathe in, breathe out. It will be okay. Don't worry. Mhm. In fact, our assumptions about jobs arriving at the same time could prove SGS is an optimal scheduling algorithm. However, and this is the favorite part of everyone, the however part. You are in a systems class, not theory, or operations research. No proofs are allowed. Thus, we arrive upon a good approach to scheduling with SGF. But our assumptions are still fairly unrealistic. Yes, let's relax another. In particular, we can target assumption 2 and assume no jobs can arrive at any time instead of all at once. What problems does this lead to? Another pause at any time. Yes, the long task could come first, then after a hair be after it, a hair time, or how did they say it? After just a split nanosecond, the other short ones come. So they have to wait for the one. Okay. Yes, I think this is it. May we do this? Okay. Okay, just a hair before, a hair after. Okay, let's say that A came first. Here, A came first, then a hair after it came. We got B and C came after at the same time, or like, you know. Uh-huh. Where is it? Okay. How can we illustrate the problem again with an example? This time A arrives at t is equal to 0 and needs to run for 100, whereas B and C arrive at t is equal to 10 and each need to run for 10 seconds. With pure SGF, we'd schedule the scene, okay, like this. SGF with late arrivals from B and C. Even though, okay, what can a scheduler do? Shorted time to completion. I was thinking about, for example, if this come and there is this, the time to complete is larger than the time to complete for this. For example, here it will be 90. Just stop this, then run these first, then continue. I think. Shortest concerns, okay. Jobs must run to completion. So let's do that. I need to go to the toilet. Okay. To address this concern, we need to, okay. Jobs must run to completion. So let's do that. We also need some machinery within the schedule itself. As you might have guessed, given our previous discussion about timer interrupts and context switching, the scheduler can certainly do something else when BNC arrive. It can preempt job A, decide to run another job, perhaps continuing A later. SGF, by our definition, is a non-preemptive scheduler and thus suffers from, okay. Fortunately, there is a scheduler which does exactly that. Add preemption to SGF, known as shortest time to completion first, STCF, or preemptive shortest time. PSGF. Okay, anytime a new job enters the system, the STCF schedule determines which of the remaining jobs, including the new job, has the least time left. Okay, and schedule that one. Little break. Okay, I am back. Anyway, uh, okay, so we are here. Fortunately, there is a scheduler which does exactly that. Add a preemption to SGF known as okay. Anytime a new job enters system, TCF schedule determines which of the remaining jobs, including the new job, has the least time left and schedules that one. Thus, in our example, we will preempt A and to run B and C to completion, and when they are finished, A the running time will be scheduled, shown as an example. Okay. Anyway. Okay, just 50 seconds. It's probably optimal. New metric, response time. Thus, if we know job length and the job only used the I am eating while studying, so so if we knew job lengths, the jobs only used the CPU, and our only metric was journal time, STCF would be a great policy. In fact, for a number of early batch these types of scheduling algorithm made some sense. However, the introduction of time shared machines changed all that. Now users would sit at a terminal and demand interactive performance from the system as well. And thus a new metric was born, response time. We define response time as the time from when a job arrives in the system to the first time it is scheduled. For example, if you had to schedule from figure 7.5 with A arriving at time 0, For example, if we had to schedule film figures 7-5 with A arriving at time 0 and B and C at time 10, the response time of each job is as follows. 0 for job A, 0 for job B, 10 for job C. As you might be thinking, and are not particularly for response time. If 3 jobs arrive at the same time, for example, the third job has to wait for the previous 2 jobs in to run their entirety before being scheduled just once. While great for turnaround time, this approach is quite bad for response time and interactivity. Indeed, imagine sitting at a terminal, typing and having to wait 10 seconds to see a response from the system because some other job got scheduled in front of yours. Not too pleasant. Okay, this is a good advice. Good what? Good remark. Thus, we are left with another problem. How can we build a scheduler that is sensitive to response time? Round robin. Round robin, round robin. To solve this problem, we'll introduce a new scheduling algorithm, classically referred to as round robin. Scheduling, the basic idea is simple. Instead of running jobs to completion, round robin runs a job for a time slice, sometimes called a scheduling quantum, and then switches to the next job in the run queue. It repeatedly does so until the jobs are finished. For this reason, round robin is sometimes called time slicing. Note that the length of a time slice must be a multiple of the timer interrupt period. Wait. Yeah, this is must be a multiple of the time interrupt period. Because if the time interrupts every time 10 milliseconds, time slice could be 10, 20, or any. Okay. Okay, so. To understand a round robin in more detail, let's look at an example. Assume the 3 jobs A, B, and C arrive at the same time in the system, and that they wish to run for 5 seconds. An SGS scheduler runs each job to completion before running another. In contrast, round robin with a time slice of 1 would cycle through the jobs quickly. The average response time of round robin is 1. For SGF, the average is 5. Okay, as you can see, the length of the time slice is critical for round robin. However, making the time slice too short is problematic. Suddenly, the cost of context switching will dominate overall performance. Thus, deciding on the length of the system of what? Mm, Suddenly, wait. Wait, as you can see, the length of the time slice is critical. Okay. Just deciding the length of the time slice presents a trade-off to a system designer, making it long enough to amortize the cost of switching without making this so long that the system is no longer responsive. Note that the cost of context switching does not arise solely from the OS actions and saving there's time few registers. When a program runs, they build up a great deal of state and CPU caches, TLBs, branch predictors, and other on-chip hardware. Switching to another job because this state to be flushed to a new relevant, state relevant onto the currently running job to be brought in, which may exact and noticeable permanent cost. Okay, round robin is a reasonable time slice. Without it, it does an excellent scheduler if response time is our only metric. But what about our old friend turnaround time? Let's look at our example above again. A, B, and C each with running times of 5 seconds. They arrive at the same time and are scheduled. Okay. You can see from the picture above that A finishes at 13, 40, and for an average of 14. Pretty awful. It is not surprising then that is indeed one of the worst policies of turnout is our metric. The first one, 5, 10, 15. Okay, intuitively this should make sense. What RI is doing is stretching out each job as long as it can, but only running each job for a short bit before moving to the next. Because turnaround time only cares about when job finishes, is nearly pessimal, even worse than simple FIFO in many cases. Mhm. So more generally, any policy such as RR that is fair, i.e. that evenly divides the CPU among active forces on a small time scale will perform poorly on metrics such as turnaround time. Indeed, there is an inherent trade-off. If you are willing to be unfair, you can run shorter jobs to completion, but at the cost of response time. If you instead value fairness, uh, response time is lowered, but at the cost of turnaround time. This type of trade-off is common in systems. You can't have your cake and eat it too. We have developed two types of schedulers. The first type, SGCF, optimizes turnaround time, but is bad for response time. Second type, from response time, but is bad for turnaround time. And we still have two assumptions. We need to be the jobs do no IO. That is known. But wait, so we had which metric? Response time and turnaround time. Did we have thematics? Did I am I hallucinating? What is it? We had turnaround time, response time. Wait. Okay. uh, okay. When possible, overlap operations to maximize these systems. Overlap is useful in many different domains, including when performing disk I/O or sending messages to remote machines. In either case, starting the operation and then switching to other work is a good idea and improves the overall utilization and efficiency of a system. Of the system. Response time is lowered, but at the cost of turnaround time. This type of trade-off is common in systems. You can't have your cake and eat it, okay? The job does no I/O, and assumption 5 that the run time of each job is known. Okay, incorporating I/O. First, we will relax assumption. Of course, all programs perform I/O. Imagine a program that didn't take any input, that will be produce the same output each time. Imagine one without output. It is the proverbial tree falling in the forest with no one to see it. It doesn't matter that it's run. A scheduler clearly has a decision to make when the job initiates an IO request because the currently running job won't be using the CPU during the IO if it is blocked. Okay, waiting for the IO completion. If the IO is sent to a hard disk drive, the process might be blocked for a few milliseconds or longer, depending on current IO. If the IO is sent to a hard disk drive, the process might be blocked for a few milliseconds or longer, depending on. Thus, the scheduler should probably schedule another job in the CPU at the time. Okay, the scheduler also has to make a decision when the IO completes. When that occurs, an interrupt is raised. Wait, let me see the. I just had the minus 12 volts. I just see the drivers part. Where is drivers? Shower, DAX, external, media, net, NVMe. Okay, let's see this. Host, target, key config, make file. Okay, let's see host. Wait, constants, core, fc, nvme.h. Quick name. Yeah, this is tcp.c. What the hell? TCP. This is tough, man. 3000 input joystick keyboard. Okay, let's see keyboard. Apple Spy. D-Link. Okay. Oh my god. Is this like, does it have a driver for literally every single keyboard on earth? No. There are some keyboards here that I don't know. Or maybe the models of drivers, maybe. Uh, okay, let's see. Apple Spy. Let's see. Max Fingers 11. Okay. Uh, this is weird. Mm, why would you make the max fingers 11? Why not 10? We have 10 fingers, right? Keyboard protocol. Oh my god. Yep. Mouse. Let's see mouse. Make file. Synaptic vMouse. VMouse. Let's see this. There are some files keyconfig OSC in it. Mouse. Is this like a custom scripting language for the kernel? Makefile. Does each directory has a makefile? Probably yes, because maybe putting everything in one folder is going to be madness. Siap objects. It compiles everything as object files. Okay, okay. Anyway, locked. Okay. The scheduler is probably schedule another job on the CPU at the time. The scheduler also has to make a decision when the I/O completes. When that occurs, an interrupt is raised, and the operating system runs and moves the process that issued the I/O from blocked back to ready state. An interrupt is raised. This is literally just kernel work is just knowing how the hardware works somehow, maybe. But this is what it looks like. All of them have interrupts. And OS runs and moves the process, the issue, okay. Of course, it could even decide to run the job at that point. How should the OS treat each job? To understand this issue better, let us assume that we have two jobs, A and B, which each need 50 milliseconds of CPU time. However, there is one obvious difference. A runs. Wait. I read this and I didn't even understand what. I'm just because I'm feeling sleepy. Okay, the scheduler has also to make a decision when the IO completes. When that occurs, okay. And OS runs and moves the process that issued, okay, of course. It could even decide to run the job at that point. How should the OS treat each job? To understand this issue better, let us assume that we have two jobs, A and B, which each need 50 milliseconds of CPU time. However, there is one obvious difference. A runs for 10 milliseconds and then issues an IO request. Assume here the IOs take each. To understand this issue better, just assume that we have two jobs, A and B, which each take 50 milliseconds of CPU time. However, there is one obvious difference. A runs for 10 milliseconds and then issues an IO request. Assume here the IO takes 10 milliseconds, whereas B simply uses the CPU for 15 seconds and performs no IO. The scheduler runs A first, then B after. Assume we are trying to build shortest task. What? Is this shortest task come first? I have no idea. Let's duplicate this. SGCF. Shortest time to completion first. Okay. Assume we are trying to build shortest time to completion first. Schedule. How should such a scheduler account for the fact that A is broken up into 5 10 millisecond sub jobs? Wait, A runs for 10 milliseconds and issues an IO request. Assume here that IOs each take, okay. Okay, so the word in here is not clear. It said that like it means like A runs for 10 milliseconds, then issues an IO repeatedly. Run for 10 milliseconds, perform IO, 10 milliseconds, perform IO, and so on, 5 times. The scheduler runs A first, then B after. Assume we are trying to build shortest time to completion per scheduler. How should such a scheduler account for the fact that A is broken? Let me think. Let me think about this. I think it will become like a round robin. Run A for 10 milliseconds, then B, then A, then B, then A, then B, and so on. Uh, okay. Whereas B is just CPU domain. Clearly, just running one job and then the other without consideration how to take IO into account makes a little sense. Okay, okay, this makes sense. This is what I thought. I mean, because it was obvious, I thought maybe there is something better. A common approach is to treat each 10 millisecond subjob of A as an independent job. Thus, we know the system starts its choice whether to schedule a 10 millisecond A or 15 millisecond B. The chart system. Choose the shorter one in this case, then and first subjob is completed, only B is left. While waiting for the IO of another process to complete. The system is thus better utilized, and thus we see how a scheduler might incorporate I/O by treating each CPU burst as a job. The scheduler makes sure processes that are interactive get run frequently, uh, while those interactive jobs are performed I/O. Other CPU-intensive jobs run, thus better utilizing the CPU, the processor. No more Oracle. No more see in the future how long the process runs. With a basic approach to I/O in place, we come to our final assumption that the scheduler knows the length of each job. As we said before, this is likely the worst assumption you could make. In fact, in a general purpose OS, uh like the ones we care about, the operating system usually knows very little about the length of each job. Thus, how can we build an approach that behaves like SGF or STCF without such a priori knowledge? Further, how can we incorporate some of the ideas that we have seen with round robin schedulers so that response time is also quite good? So without such a further, how can we incorporate some of the ideas that we have seen? Okay, summary. We have introduced a the basic ideas behind scheduling, and developed two families of approaches. The first runs the shortest job remaining and thus optimizes turnaround time. The second alternates between all jobs and just response time. Both are bad where the other is good. Alas, what? An inherent trade-off common system. We have also seen how we might incorporate I/O into the picture, but we have not still resolved the problem of the fundamental inability of the operating system to see into the future. Shortly, we will see how to overcome this problem by building a schedule that uses the recent past to predict the future. This schedule is known as multi-level feedback queue, and this is the topic of the next chapter. Okay, homework simulation. This program scheduler Pi allows you to see how different schedulers perform under scheduling metrics such as response times and no. See read me for details. Okay, let's see this homeworks. Wait, let's see this project. Concurrency, stored, checks, distributed, reverse, schedule lottery, process. This. Anyway, homework. Schedule run KPD. What? What is this? Is this okay? It is the same one we just read. Schedule of the spy. Remove this. Clear. Let's move from downloads. What was its name? Homework. Okay. Let me remember how does it work. Ouch. What? No, ouch. Okay. This clear. Ouch. Okay, so ouch. Decompress. Okay. Let's see the host scheduler. Yes. And then here hidden scheduler. Right? Solution. Wait. This program scheduler spy allows you to see how different schedulers perform under scheduling metrics such as response time, turnaround time, and total wait time. The scheduler are implemented. FIFO, SGF, and round robin. SGF shortest. Wait, SGF? I cannot remember all of these. SGF. Shortest job first. So okay. Whatever. Okay, there are two steps to running the program. First, run without the C flag. This shows you what problem to solve without revealing What problem to solve without revealing the answer. If you want to compute the response, general and return errors around it. What? Wait, what? Is there a syntax error? Why does it look? Does this look like Lua? Oh my god. What the hell is this? What? 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 Python 2. Okay, search Python 2. Python 2. Okay. Run. Okay, just do it this. What does this do? FIFA. Argjobs 3. Max length 10. Seed 0. Here is the job list with the runtime of each job. Job 0. Job 1. 8. Job 2. 5. Compute the turnaround time, response time, and wait time when you are done. Okay, this is with FIFO. With the same, but sir. Okay, turnaround time. Turnaround time is just first in, first out. So it is 9 times 3 plus 8 times 2 plus 5. Okay, so 9 times 3 plus 8 times 2 plus 5. 48 divided by 3. Wait, it is 8, okay. So it is 48 divided by 3, it is 16. So the turnaround time is 16. The response time is 0 plus 8. Okay, so we have, okay, so 16. We have 8 plus plus 9 plus 8. Which is 25. Yes, 25. And wait time, no, the response is wait time when you are done is the same, but let's see. Okay. What is this? Wait time. What is wait time? Let's find wait time. Okay, let's see if wait time. Wait. Any time spent ready but not running. Okay, this makes sense. Okay, any time spent not running while ready. Okay, so we have this 0, 9, 8. Okay, 9 plus 8 is 17, and 17 plus 5, not really, doesn't matter. The first one does not wait at all. The second one waits 9. The third one waits 9 plus 8. Okay, so it is 9 plus 17, which is 26. Okay, I'll just wait, how do I specify the run command? Python 2. What? I hate this. Python. I know you guys are going to find a lot, but it's whatever. Python 3, 3, 3, 3, 3, 3. Python. What the hell is this? Stupidest thing ever. Fuck is this? Okay, where is the run command? Oh my god, finally. Let's see. Okay, just stop. Problems. Can I just find some respectable Python? Oh my god, leave this. Execute. Oh my god. Wait, can you just give me a. Oh my god. Fuck this shit. No, sure. If your code requires import, edit here before then. What? How slow should this be? What? Yeah. Python 3. I just ask AI to convert to Python. I hate this stupid website. I want to copy. response time, turnaround, wait, average, turnaround is 16, okay, wait, I don't get it. Response time is 0, response time is 9. 9 plus 17. Oh, I forgot to divide by 3. The response time is turnaround is response is 0 plus 9 plus 17, which is 26 divided by 3. 26 divided by 3. Okay, the wait time is 9 plus 17, which is also 26 divided by 3. Okay. It's easy, I guess. Okay, let's see the rest. There are 2 steps to running the program. Okay, FIFO. This specifies the FIFO policy in a specific random seed of 100. If you want to see the solution for this exact problem, you have to specify the exact same random seed again. Let's run it and see what happens. This is what you should see. Prompt scheduler. Okay. Okay. This is. I don't think I should spend a lot of time on this. It's not even hard. You know what I mean? Wait, compute the response time of the running 3 jobs of length. Okay, when they are equal, whatever. We finished CPU scheduling, now multi-level feedback. Q. Copy, let's paste it here. Okay. Stupid online interpreters. Should we stop right here? Maybe we should. Yes, maybe we should. Just do this. Yes. Create summary for this. Main audit. First come, first serve FIFO. But a long job can delay many shots. Okay. Shortest job first. Runs the shortest job first. Minimize average turnaround time when all jobs arrive together. But it is not preemptive. Preemptive SGA. Shortest time to complete first. Always run the job with least remaining time. Improving turnaround and short are okay. Gives each job a small time slice, good for response time and fairness, but usually worse turnaround time. Very short times slices increase context switch overhead. For IO bound workloads, the scheduler should run another process while one waits for IO. For IO bound workloads, the scheduler should run another process while one waits for IO. Overlapping CPU and disk work to improve visualization. Okay. The central trade-off is better turnaround and better response time. Of original operating systems do not know future job lengths, so later schedule estimate behavior from a process instance. Okay. How long have we been there? Okay, 7 hours and a half. I think this is it for today. Maybe I will read the first bit of this so I can reread it again later. And just now reading it will give me like some kind of confidence that tomorrow will be easy, you know. In this chapter, we'll tackle the problem of developing one of the most well-known approaches to scheduling, known as MLFQ. The multi-level feedback queue scheduler was first described by Corbato. Okay, in 1962 in a system known as compatible time-sharing system. And this work, along with later work on Multics. By the way, Multics is like from where Unix got its name. Since there was some company named Multics, some people wanted to start a new operating system and name it as Unix. You know, kind of opposite, multi-unique. Anyway, This is what I read somewhere. Led the ACM to award Gorbachev its highest honor, the Turing Award. The scheduler has subsequently been refined throughout the years to the implementations you will encounter in some modern systems. Does Linux now use MLFQ? Uh-huh. Fair scheduling class now based on earliest eligible to the virtual deadline first. Track each task entitled CPU share using virtual runtime and selects the it achieves some goals similar to MLFQ and such as fairness and good intellectual latency, but the mechanisms differ. Several explicit priority queues are then scheduled as instructions to the queue. Tasks move between queues. CPU heavy tasks are commonly denoted. CPU usage change a task age and virtual condition. Interactive tasks retain or gain priority. Sleeping tasks can receive however if it is fixed contact per queue. Okay, this is tough. Just to understand, I don't understand any of this. Okay. The fundamental problem MLFQ tries to address is twofold. First, it would like to optimize turnaround time, which, as we saw in the previous note, is done by running shortest jobs first. Unfortunately, the OS doesn't generally know how long a job will run for. Exactly the knowledge that algorithms like SGF require. Second, MLFQ would like to make a system feel responsive to interactive users. Users sitting and staring at the screen, waiting for a process to finish, and thus minimize the response time. Unfortunately, algorithms like round robin reduce the response time but are terrible for turnaround time. Thus, our problem given a problem which is given that we in general do not know anything about a process. How can we build a scheduler that achieves these goals? How can the scheduler learn as the system runs? The characteristics of the jobs it is running and thus make better scheduling decisions. How to schedule without perfect knowledge? How can we design a scheduler that both minimizes response time for interactive jobs while also minimizing turnaround without a priori knowledge of the job length? Okay, learn from history. The MLFQ is an excellent example of a system that learns from the past to predict the future. Okay, such approaches are common in operating systems and many other places in computer science. Okay, including hardware branch predictors and caching algorithms. Such approaches work when jobs have phases of behavior and thus are predictable. Of course, one must be careful with such techniques as they can easily be wrong and drive a system to make worse decisions than they would have with no knowledge at all. Okay. Milky basic rules. To build a scheduler, in this chapter we will describe the basic algorithms behind a multi-level feedback queue. Although the specifics of many implemented MLQ differ, Most approaches are similar in our treatment. The MLFQ has a number of distinct queues, each assigned to a different priority level. At any given time, a job that is ready to run is on a single queue. MLFQ's priority decide which job should run at a given time. A job with higher priority is chosen to run. Of course, more than one job may be on a given queue, and thus have the same priority. In this case, we'll just use round robin scheduling among those jobs. Thus, we arrive at the first two basic rules of MLFQ. If priority of A is higher than priority of A and B doesn't. If priority of A, okay. The key to MLFQ scheduling therefore lies in how the scheduler sets priorities. Rather than giving a fixed priority to each job, MLFQ varies the priority of a job based on its observed behavior. If, for example, a job repeatedly relinquishes the CPU while waiting for input from the keyboard, MLFQ will keep its priority high, as this is how an interactive process might behave. If instead a job uses the CPU intensively for a long period of time, MLFQ will reduce its priority. In this way, MLFQ will try to learn about processes as they run and thus use the history of the job to predict its future behavior. If we were to put forth a picture of what the queues might look like at a given instant, we might see something like the following. Figure 8.1, page 3. Right, if we were to put forth a picture of what queue might look like, we might see something okay. Two jobs A are the highest priority level, while job C is in the middle, and job D is at the lowest priority. Given our current knowledge of how MLFQ works, the scheduler would just alternate time slices between A and B because they are the highest priority jobs in the system. Poor jobs C and D would never get to run an outage. Of course, just showing a static snapshot of some queues does not really give you an idea, okay? But we need to understand how jobs change priority over time, and that in a surprise only to those who are reading a chapter from this book for the first time is exactly what we need next. Okay, Q1, Q8. AB will be running round robin. K, C, and D. How to change priority? We now must decide how MLFQ is going to change the priority level of a job, and thus which queue it is on over the lifetime of the job. To do this, we must keep in mind our workload. A mix of interactive jobs that are short running and effectively relinquish the CPU, and some longer running CPU bound jobs that need a lot of CPU time, but where response time isn't important. For this, we need a new concept, which we will call the jobs allotment. The allotment is the amount of time a job can spend at a given priority level before the scheduler reduces its priority. For simplicity, at first, we will assume the allotment is equal to a single time slice. Here is our first attempt at priority adjustment. Okay, this needs this needs way more focus than I have right now. That's why this is enough for today. Goodbye.